Let's discuss this question, maximum number of moves in a grid. Basically, we need to calculate what is the maximum number of move we can make. So let's understand this question. So basically, we can start from any of this element, that is any element in the first column we can start, and we can move to so suppose we take this element, we can move either here or either here or either here. So these are the three possibilities, and we can move only if the element to which we are moving, or the cell to which we are moving, the value of that cell must be greater than this value from where we are moving. So if we look here, can we move from here to here? No. Can we move from here to here? No. Can we move from here to here? No. But can we move from 2? Can we move to here? Yes. From let me just clear things out. From 2, can you move here? Can you from 2, can you move here? Yes. Let's check one more example as these values are equal. From 9, can you move here? No, because this value should be greater than 9. Can you move here? No, again these values should be greater than 9. Can you move here? The answer is yes, we can move. So given these constraints, we need to figure out what are the maximum number of moves possible actually. So how we can solve this actually? So to solve this, we can think. Suppose we are here. Just an instance, we can move either here or here or here. Ideally, if the condition matches. But as the condition does not matches, so we'll be able to move only to here. But let's think of a scenario that we are able to move to here as well, here as well, here as well. Now, at this stage, if we know what's the maximum number of moves this and this cell are having, we'll move only to that cell, because for this particular cell it will be maximized only when we know uh, what is the maximum number of moves to these cells, and we'll take the maximum to it, and we'll basically move to the maximum cell. So just an instance, so suppose it doesn't so firstly it does not coincide with this example. Suppose we have 4 moves here, 5 moves here, and we have 6 moves here, and from this cell we can move to this one and this one. Which one we'll take? We'll obviously take this one, because if we move to here, uh, so what is our move score? So this score was already 6. Now we are all and from here we are moving to here, for 4 it is 7. So we need to solve in this way. And what is the base case? So when we reach here, when we reach this column or the end column, we don't have any option to move. We cannot move to here, like we cannot move anywhere, because we don't have any element present after the last column. So we cannot move. So for base case, we can say, so let's take a matrix. So let's take a matrix which corresponds to this. Basically, so for all this it will be 0, and if we find and from this cell, if we can move, if we have the if we meet the condition that we can move to this or this, we will take any of this. The reason being that all are 0, so we can just take any of this. Now how we can solve this? So we can build a recursive approach based on the logic that I discussed, or or there are overlapping problem for this. So if you see, for this last column it will always be 0, right? Now in the second last column we can move, if we have the possibility to move, the answer will be 1. Suppose here answer is 1. Now in the next column, if we have possibility to move any of this, we can just simply add up the value that is present over here. Add 1 to this value, and this will be the result for the this column. Likewise, we can solve this using dynamic programming actually. So now let's look into the code for better understanding. Let's try to visualize this code, what we are doing. So first we are creating a two-dimensional DP matrix. So this is our matrix actually, and all the elements are initially 0. All the elements are initially 0. Now as we know, we are going to update these cells. I am not mentioning them 0 because they will be updated if found feasible. So we start from j n minus 2. So basically this is n minus 2 dot 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 dot, this is 0. We go up to here, and for every j we actually iterate over all the rows. So we start from 0 and go up to m. This we do. So first we verify. So from each cell we can go to next column, and row wise we can go to I minus 1, I, or I plus 1. So we see uh, so these are the possible cells or the row that we can traverse for a row or the I. So we see if I is if a is greater or equal 0. So this validation is only for, so that we don't go beyond this cells. Like if we are here and we are doing minus 1, a equals to my I minus 1, we are going to minus 1, which is not feasible. We check this basic condition. After that we try to look into the grid values that we are given. If it matches the condition, that is or the constraint which is mentioned in the question, then only we update our R max value, which was previously minus 1, and try to get what's the maximum. Suppose you are here and this matches the condition, and we try to get the maximum of these three. The maximum of these three we take and add 1 to it if R max not equal to minus 1. Why R max not equal to minus 1? Because R max we set it initially to minus 1, and if it is minus 1, that means none of these cells from here does not matches the constant which is mentioned in the question, so it will still be 0. Now we traverse, after we have built up this solution, we traverse this first column and try to get what's the maximum value, and we just return it. Again, it can be optimized in terms of space. So we so if we are here, right, if we are here, we are only referring to this column, so there is no need to maintain the whole, like all these columns. So once it's utilized, we can replace with this one and again calculate. So we can optimize the space in this way. Thank you.